All right, good afternoon, and thank you for joining us for the December DuraMAT webinar. We're excited to have you. Before we get to the good stuff in the presentation, I just have a few quick housekeeping items. My name is Harrison Dreves from the NREL Communications Office, and I'll be managing the technical support for today's webinar. Next slide, if you don't mind. Just a reminder that this webinar everyone is muted. We're just going to be listening to the presentation here in the room. If you're online, you can join through two different options. You've got phone or computer. Computer works great 99% of the time. If you're in that 1% having a bad day today, you can always listen by phone. Either choose the phone option or just leave and rejoin. And when you rejoin, you can join by phone. Next slide. If you're having technical issues, audio or otherwise, please use that chat button at the bottom of the screen to chat me. I'll be keeping an eye on that all webinar, and I will help you get connected. We're also recording today's webinar, and it should be available on the DuraMAT website in a week or two. So if you miss anything, fear not, you'll be able to watch it later. If you have a question for Dana, we are going to be taking questions at the end of the webinar. We ask that you put those in the Q&A tab. That is the speech bubble with a question mark icon in the bottom toolbar on Zoom. Please use that to submit questions. You can submit them at any point during the webinar, and we'll ask them at the end. So to reiterate, tech support issues, chat, questions, Q&A. Please don't put questions in the chat panel if you can avoid it. All right, with that, I'll hand it over to Michael Owen-Bellini, who's going to introduce our speaker today.
Great.
Michael.
Thank you, Harrison. So welcome everyone to this month's DuraMAT webinar. I'm Michael Owen-Bellini, I'm staff scientist at NREL and part of the DuraMAT leadership team. We host these webinars monthly on a variety of topics relevant to DuraMAT's activities. Next month's webinar will be focused on the upcoming iteration of the Technology Scouting Report presented by Eli Palmielti and other authors on that work. And I think, Harrison, do you have a registration link that we can provide for that?
Okay.
But this month's webinar will be presented by Dana Kern. Dana did her undergraduate at MIT and PhD work at the University of Washington, Seattle. Her research at MIT and UW focused on molecular photophysics and organic photovoltaics. She came to NREL in 2018, began working in PV reliability using electro-optical imaging characterization techniques. Her work in PV reliability and DuraMAT focuses on characterization of PV degradation modes in field PV modules, as well as assessing materials interactions in PV cells and packaging using accelerated stress tests. So today, Dana will be talking about sequential stress testing of bifacial modules. Take it away, Dana.
Cool. All right, thanks. Hi, I'm Dana Kern, and I'll go over sequential stress testing to identify processing defects in bifacial photovoltaic modules. So to start out, a bit of background on stress testing. Product qualification tests like IEC 61205 or 61215 have been created to screen for design flaws or early failures. This is ideal to find known degradation modes in existing technologies, but now as people are transitioning to new packaging designs, advanced cell types, and targeting longer warranties, things like combined and sequential stress testing have been getting more interest. There are some distinct advantages like being able to better mimic outdoor conditions by having multiple types of stressors, potentially decreasing the number of parallel samples or tests that you have to run, and avoiding unrealistic conditions, for example, by overextending single factor stressors. So on the slide, we have some examples of different types of sequential or combined stress factors in the community. So there's PVEL's product qualification program at NREL. There's CAS, the combined accelerated stress testing. There are other things like here by DNV and DuPont for module accelerated sequential stress, and IEC has some sequences for sequential stressors. So today we'll go over some case studies of sequential stress based on a modified sequence of IEC 63209-2. These are 3 different case studies we'll go through, all using the same type of sequential stress. So we'll look at impacts of processing defects on glass or glass transparent backsheet mini modules, where loss was dominated by delamination or resistive changes. We'll look at another example where the cells were unstable. So there's a rear side passivation loss dominated by surface recombination on the back side of the cells. And then a third example where nothing's actually wrong with the samples. And so we target trying to understand impacts of encapsulants and intentional design changes like cell cutting. But this is actually good news for us when module materials are good and you actually don't see a whole lot of degradation. So here's a summary of the experimental setup that's roughly followed for all of these different case studies we'll go through. We have a set of samples that gets aged outdoors and they get periodic non-destructive characterization. There's also control samples that sit inside in the closet and they get parallel characterization along with the other tests. And then we have duplicate sets of samples that go through accelerated stress testing. These little ND icons are non-destructive characterization points. So that includes current voltage curves, external column efficiency, photoluminescence, electroluminescence, dark Lock-in thermography, and UV fluorescence. The sequential stress steps include damp heat for 200 hours. Then the sample batches split to either get front side light exposure or rear side light exposure. This is a full spectrum of light, including the UV portion. And if the front side is exposed, it's about 2,000 hours of exposure or 1,000 hours on the rear side. Then those sample batches come back together for thermal cycling for 50 cycles, humidity freeze for 10 cycles, and then repeat that stress sequence for as many times as you need until degradation happens. Then they exit that loop with 200 hours of damp heat, and then a final light exposure step that's a little bit shorter. So there's a lot going on there, and I like to think of it in pictures so you don't get lost. So you can just think of it as wet, sunny, hot, cold, then wet and sunny again. So the first example is processing defects. So this is a sample set that had some non-optimized sample fabrication. We have glass samples and glass transparent backsheet samples, both single cell mini modules. The lamination was not optimized for the glass construction, and so these glass samples do have edge pinch, causing this tensile stress around the perimeter, like I'm showing in that schematic down here. That stress around the perimeter results in cavitation and delamination, like you can see here in the photos of the mini module corners. We have little bubbles, or like here you can see the glass texture where the sample has already started delaminating before any stress was applied. Transparent backsheets don't have this particular problem because the backsheet can conform to the back of the sample as needed, so it kind of relieves that stress. However, there could be other limitations for transparent backsheets associated with polymer durability, especially if those backsheets are directly exposed to UV containing light. And then before we go forward, we will note that this is not representative of all glass or all glass transparent backsheet constructions, but it's just a useful case study to see the impact of processing defects when they do exist. So I drew these glass samples as being kind of a bowed shape, and we do characterize that to show that that's actually the case in these mini modules. So this is how we do that using some machining tools. And then once we have that data, so first, where's my pointer? It went away. There it is. First, we measure the surface bowing like I showed you in that video, and then perform polynomial surface fits to these samples to kind of understand their shape parameters. Then you can calculate an overall shape parameter for the sample based on these surface fits. So based on that process, for the glass transparent backsheet mini modules, they're shaped like a saddle or a Pringle, as shown over here by these negative K values, or the glass samples have a peak shape, which looks kind of like a football. So one surface like that, the other surface like that. So that just confirms that in this particular mini module fabrication, we do have this impact of edge pinch that you can confirm with this shape. And this, the impacts of that will be further discussed in this upcoming paper from our group for best practices in mini module fabrication for lab scale testing. So then the question is, how did these samples do outside? We had a set of mini modules aging outside and saw that the degradation rates were somewhat high, but not unreasonable. The mini modules were held at the maximum power point, with the maximum power point being measured every 5 seconds, and then outdoor IV curves every 30 minutes. The annual degradation rates were calculated both from this outdoor data and from taking the mini modules inside for flash testing. So Dirk Jordan took the outdoor and maximum power point data, did analysis using clear sky filtering and RD tools to get the degradation rates shown as these black dots. And then Sonia Olichna would take these mini modules inside every 1 to 2 months to do a flash test and fit a linear degradation rate to that to get the data points shown here as the gray circles. So both methods gave similar degradation rates for these modules aging outdoors. And overall, we see there is a slightly higher degradation rate for the glass mini modules compared to the glass transparent backsheet ones. And that's just consistent with those initial processing defects in the glass mini modules. So now what happened to the mini modules after accelerated stress testing? This is after the entire sequence of accelerated stress testing, just looking visually how the mini modules have degraded. So with the sequence containing front side light exposure, we see delamination that's particularly bad in the glass POE samples, and the delamination progresses on the side that was exposed to light. So you can see that over here where there's this pattern of the inside textured surface of the glass, and that's extending over the front side of the mini module. But when you look at the back side, you don't see the delamination pattern. For the glass transparent backsheet samples, we saw a lot of polymer yellowing, and that's seen over here. And you can even see in the glass transparent backsheet POE mini modules, there was more significant yellowing in the areas carrying current, so on these ribbons, the busing ribbons. We saw solder pad corrosion on the rear side of the glass transparent backsheet sample. So the silver part of the solder pad is right about there, and it becomes more yellow with aging. For rear side light exposure, again, we saw delamination that was particularly bad in the glass POE or glass transparent backsheet POE samples, and that delamination progresses on the side that was exposed to light. So here you see that texture of the glass surface is kind of going behind the cell, and when we look at the back side of the mini module, that's the side that's delaminating for these glass POE samples. And then pretty significant delamination here for the glass transparent backsheet POE samples as well. We saw again polymer yellowing for the backsheets, especially when the backsheets are directly exposed to light, and solder pad corrosion for the glass transparent backsheet samples, but in this case also for the glass samples when that delamination progresses over top of a solder pad. So this is showing you how the power degradation looks for these different accelerated stress tests and for the outdoor samples. Again, consistent with the visual degradation that we were seeing, we have greater degradation of the glass samples compared to the glass transparent backsheet samples when there is front side light exposure. And we see a bit more degradation of glass POE samples that starts to take place in the second stress cycle. For rear side exposure, initially we do see greater degradation for the glass samples compared to glass transparent backsheet, but then around the second stress sequence at this humidity free step, there's a pretty catastrophic degradation of the glass transparent backsheet samples, particularly for the POE one. Outdoors, we see this is somewhat consistent with the indoor test because there's more degradation for the glass samples compared to the glass transparent backsheet samples. But one difference from the indoor test is that we see greater degradation for the glass EVA compared to glass POE. So that's kind of swapped. If you look up here, there's a little more degradation for the glass POE case for both of our indoor stress sequences. So that could just be sample to sample variability. We might not have enough statistics here to really be able to say which one should be degrading more, or there could be something missing for the indoor stress sequence. So those are both options. So then we can look into the IV curves to understand why the glass sample degradation is different from the degradation of the glass transparent backsheet samples. So here are the IV curves, and we see for glass samples, there's a decrease in the shunt resistance, along with some increase in the series resistance too. But for the glass transparent backsheet samples, they're mainly dominated by an increase in series resistance, and we don't see a decrease in shunt resistance for those. So even though both of them are degrading by fill factor loss, the underlying cause of the fill factor loss is slightly different. So this is just plotting the relative changes in those resistance values for the different types of mini module constructions. So for glass samples, well, I guess for all of them, we're seeing an increase in series resistance, but we only see a decrease in shunt resistance for the glass samples. This looks like the shunt resistance is increasing for the transparent backsheet samples, but you don't have to think of that as a degradation because that's not a bad thing for the mini module performance. So then to understand why the modules are degrading more, we collect electroluminescence and photoluminescence images at each step of the sequential stress sequence. So these are going vertically here. These are all the different stress steps as the modules are degrading. And then we have all of our different sample constructions that had either front side light exposure or rear side light exposure. So it's useful to have both of these types of images because photoluminescence is mainly going to tell you if there's a problem with the absorber quality, because you're just optically exciting the sample. You don't really care about the electrical contacts to the sample as much. For electroluminescence, you're creating the luminescence using the electrical contacts. So it's really going to tell you if there's a problem with the metallization or the electrical contact to the sample. So looking at these different columns of imaging, for the most part, we see that the photoluminescence stays pretty uniform and most of our changes in the image contrast is coming from electroluminescence. So that's consistent with there being a problem in electrical contact quality, which affects the fill factor and these resistive parameters that we were just talking about. So here we're just zooming into some of those image sequences to break down what's happening in each of the different sample types. So first, we're just thinking about the degradation of these glass transparent backsheet samples. So over here, we have the image sequence for glass transparent backsheet EVA or glass transparent backsheet POE. Both of them show a similar progression that results in this kind of local brightening along the solder pads. So we start out pretty uniform with the electroluminescence images. And as you degrade, we have more local bright regions that are kind of coincident with rear side solder pads. So this is a pattern that our collaborators have modeled before, resulting from current crowding as some of your contact areas degrade. So for example, if this solder pad has degraded, then the current will have to flow through this other one and get more of a local brightening pattern. We see, so this is now the rear side exposure, but still glass transparent backsheet EVA and glass transparent backsheet POE. We see this similar kind of degradation pattern emerge with this local brightening along the solder pads, but we see that it isn't as severe until we get to this humidity freeze step kind of towards the end of the stress sequence. Then there's a pretty bad delamination event, and that really accelerates that local current crowding and degradation of some of the solder pads. Now this is the degradation of the glass samples. So we have the glass EVA and glass POE. And so we see a couple different degradation modes here compared to the transparent backsheets. So here, starting at the thermal cycling, the first thermal cycling step, you see that's where they start to diverge from the glass transparent backsheet samples. This is a sudden shunting event. And so that's where that other slope in the IV curve came from. That's different from the glass transparent backsheet ones. So that's associated with shunting at the corner areas where there's cell cracking. And then the other point where here, I guess in the second light exposure step, the glass POE samples start to diverge from the glass EVA samples. You can see the reason for that over here in the imaging, where there's a delamination event for the glass POE samples that causes more of that local current crowding around some of the other solder pads as these solder pads degrade. Then in our last step, we see a different degradation mode for the glass EVA samples, where there's a bit of a thicker darkening along these bus bars, and that is a near bus bar grid finger corrosion that I'll show you a little bit more detail in one of the following slides. So to understand the polymer degradation modes a little better, we can core out materials from these mini modules and analyze them chemically. So this is work by Sonia Ulichna, and she'll publish that in an upcoming paper. Using thermogravimetric analysis, she saw some minor deacetylation in the EVA encapsulants during aging, but as you can see over here, the degradation isn't as severe for these EVA polymers in this particular case. She did see that the POE was not very stable, and you can see that here from a sooner onset of the polymer decomposition at an earlier or at a lower temperature for the aged samples compared to the unaged materials. So even though this might not be characteristic of all POE samples, it does explain why in this particular sample set, we're seeing a lot more degradation for the POE containing mini modules compared to the EVA mini modules. She also looked into the backsheet degradation, and her conclusion is that the thin UV blocking coatings for this particular backsheet were not sufficient to protect the PET core. So she saw hydrolysis and embrittlement of this PET core in both cases for the glass transparent backsheet EVA and glass transparent backsheet POE samples. But in some cases, she saw that the backsheet could be mounted backwards, so the coatings are not symmetric. And in cases where the backsheet was mounted backwards, it could degrade more when it was exposed to the UV containing light. So this is just a summary of the different degradation modes that we saw for this part of the project. So cell cracking caused by edge pinch happened a lot more for glass mini modules compared to the glass transparent backsheet mini modules. And so there's an example of this down here where you have some cell cracking near the corners and cell periphery due to the edge pinch effect. We also saw front near bus bar grid finger corrosion that happened mainly for glass EVA and glass transparent backsheet POE glass transparent backsheet EVA, so EVA containing samples when exposed from the front side. And that shows up kind of like this, where you have kind of local darkening of those grid fingers near the bus bars. We saw rear side solder pad corrosion, basically for all of the samples, but just for varying extents. And that's characterized by this kind of local brightening along the solder pads that we see emerge quite often. Then the edge ingress grid finger corrosion happened more so for glass transparent backsheet samples and not as much for glass samples. And you can see that down here is this kind of speckled pattern that happens mostly near the edges of the mini modules. Then delamination, in this case, we had not a great POE material, so there was more delamination in the POE containing samples. So glass POE, regardless of what side it was exposed from, and glass transparent backsheet POE, very severe from the rear side. And that's a photo or image of that down here, some of those delamination patterns. So, all right, the next example we'll go over is rear side surface passivation issues. So again, we're doing exactly the same stress sequence, but we see different degradation modes happen just depending on what's wrong with the sample set. So that's an interesting feature of the sequential stress testing, that you don't have to know ahead of time really what you're targeting. It just depends on what's wrong with the samples. So in this case, we saw very severe power degradation here that happened at the light exposure step, denoted here as the A3. In this case, we saw VOC and ISC degrade, but the fill factor was unaffected. It does seem like the half cells may degrade less, but that's something we still have to look into and kind of separate out from these other features of the cells that I'll explain soon. So for samples that do degrade, the photoluminescence before degradation is nice and uniform. After degradation, it's still nice and uniform, just very dim. So that's a feature of a decreasing carrier lifetime that causes a decrease in the PL intensity. When we look at the electroluminescence here, just scaled for best contrast, you see that the contrast in the electroluminescence image is unaffected. So that's consistent with there being not much change in the fill factor, so the contact quality is fine. We're mostly just seeing a decrease in the carrier lifetime. Looking at EQE curves, external quantum efficiency. When measuring external quantum efficiency from the front side, we see a decrease in the EQE in the long wavelength region. And then measuring from the rear side, we see a decrease in the EQE in the short wavelength region. So that's a characteristic signature of a rear side surface passivation loss. So again, we have a severe loss here, mainly from a decrease in lifetime from rear side surface passivation. So to dig into this a little more, I can plot the data a slightly different way. So if I took out just the half cell constructions, you can see here we have an outlier. And so that's interesting. Why is this an outlier? If we go over to our PL images, we see that the samples that do eventually degrade start with a slightly higher PL intensity compared to the sample that eventually does not degrade. But then after degradation, the PL intensity for the sample stays the same, and these decrease a lot in their intensity. We find that this degradation is correlated with the color of the rear side surface. So here you can see that the sample that does not eventually degrade is more blue, and the samples that do eventually degrade have some gradient of yellowness. Here we have just some values that we can measure for the yellowness index, having a higher yellowness index for the samples that visually to us look more yellow or brown, and a lower yellowness index for the bluer rear samples. So this difference in the rear side color also correlates with the initial EQE parameters. So these are the EQE plots of the samples before they degrade. So the samples that do eventually degrade are shown in red, but this is before their degradation. And we see they have a lower EQE on the rear side and a lower EQE in the long wavelength region when measured from the front side. So this is already telling us that there's a problem with the rear side charge extraction. We can see that mirrored in the IV curves because there's a lower ISC when measuring the IV from the rear side and a slightly lower ISC also from the front side. However, if we look over at the VOC, there's a slightly greater VOC for those samples initially before they degrade. So this could be an indicator that maybe the manufacturer was optimizing for something like a higher cell voltage, but maybe there were other things at play that eventually lead to an unstable cell. So then to understand this degradation further, we performed extra testing of light exposure. So if you look at this sequential stress sequence, you see that there's a damp heat step here before our light exposure. So you might naturally ask, like, was the damp heat required for this degradation, or would this have happened anyway just by putting the samples under light? So in this test over here, we did the same duration of light exposure under A3 conditions. And you do see that the yellow rear cells degrade more than the blue rear cells. However, if I put them on the same scale, the same y-axis scale of the power degradation, you see that there is significantly less degradation here, only about 5% compared to these samples when they had sequential damp heat in A3. So even though this is something we want to look into further, this might indicate that this combination of damp heat with light exposure might be needed for certain degradation modes to happen. So these samples were also sitting outside, and this is their power degradation over time outside. We see a wide spread in the degradation rates across all the samples we had that could be related to them having different extents of yellowness on the rear side. We also see that the degradation overall is significantly less outside compared to the sequential stress testing indoors, and most of the degradation just happened after the first 100 days and then leveled off. So this result basically tells us that the sequential stress test is much more severe compared to a year of outdoor degradation. So we did look at segments of these yellow rear and blue rear samples to understand what the differences are on the rear side that could cause this significant degradation. So we see a much thicker aluminum oxide coating for the samples that do eventually degrade under light exposure, maybe slightly thicker nitride as well. We confirmed this result with several different characterization methods as well. And then here we're showing some of the SIMS data just to also look a little more closely at the chemical differences that there could be on the rear side. We find, interestingly, a greater hydrogen content on the yellow rear cells compared to the blue rear cells. So again, that's consistent with those cells initially having a higher open circuit voltage and slightly brighter PL. So again, the manufacturer could have been optimizing for this, just wanting a better initial voltage and using higher hydrogen for that reason. And again, we confirm here the thicker aluminum oxide coating with the SIMS data. So to conclude for those, the color changes here are from differences in those rear side thicknesses and the refractive index of this ARC coating and passivation layers. And while this might not have such a big impact, or people don't care as much maybe for the initial performance, maybe we have to understand if there are additional things going on that could relate to durability. And this is just to show that this is probably not a problem for all PERC cells. There are plenty of PERC cells that are just fine. But we do observe just some modules out in the wild that might have differences in color on the rear side. So this isn't something we've tested in modules yet, but just to note that this is out there and maybe it's something we could consider moving forward. So the third case study here is on ideally intentional changes of encapsulants and cell cutting. But we find that we've actually eliminated all of the problems in our module materials and these samples end up super stable. So we eliminated our prior issues. We have no edge pinch because we used edge supports in the lamination. We use a glass-glass construction, so there's no back sheet to have to worry about polymer degradation modes. And we have high quality cells that don't have passivation issues. The result here is that PV module materials can have good stability if you use high quality materials and good constructions. So that's maybe a boring result if you're a scientist who wants to publish things, but it's a great result for the PV community and having confidence in moving forward in the energy transition. So this is just those samples aging outdoors. Again, they have maybe about 2% degradation, but most of that degradation is happening in the first 100 days, and it's all associated with a change in ISC. So we have some suspicion that this degradation could just be an optical effect, maybe from the samples becoming dirty. So cleaning them could help us answer that question. This is the degradation of those samples again under the same sequential stress process, but this time they're so stable that we repeated this stress cycle 3 times. So this is 1 to 2 more iterations of the stress sequence compared to the previous examples we looked at. And even after all of this accumulation of stress, we only have about 5% relative degradation, regardless of if they are full cell constructions or half cell constructions. But because we're scientists and we have to overanalyze everything, here I'm pointing to one really subtle degradation mode that might be happening in these samples, which is a recoverable loss right around this 3rd cycle of TC50, so thermal cycling with 50 cycles. So it seems like we have a loss here associated with fill factor and that recovers after humidity freeze. We can look at the imaging to understand why that happens. So the degradation was most severe in the POE containing mini modules, and it seemed less severe for EPE or EVA, both for the full cells and half cells. So here, these are the POE containing full cell constructions or the POE containing half cell constructions over the course of this recoverable loss, where the loss happened at TC50. So we basically see an intensity redistribution along these busing ribbons. So here you can see pretty easily in the half cell constructions, it's largely flat. And then as you go into the spot where the fill factor degrades, you have some local intensity around some of the busing ribbons, and then it recovers after humidity freeze. So that doesn't happen as severely in the mini modules that don't have that recoverable fill factor loss. So for example, the EVA mini modules didn't show the recoverable fill factor loss, and here our intensity profiles remain pretty uniform. So I'll leave you with these for the good news. The good news is that high quality PV samples have good stability, even if in this really severe sequential stress test. But that might lead you to ask, well, how severe is this test and how do you know that it's severe? And I think that's a really hard question to answer, especially like even for single factor stressors, it's hard or impossible to extrapolate out to years outside. And now we're further complicating the situation by interweaving these stress steps. Yeah, it's a hard question to ask. But the thing I can show you is just a list of the amount of stress imparted on the samples through this modified sequential stress sequence, and compare that to maybe things that people all know and love, like the IEC 61215 design qualification. So for a lot of these stress types, like damp heat, thermal cycling, humidity freeze, that amount of stress could be comparable to things you might see in 61215. The one big difference is seeing the amount of UV containing light exposure. So there's not a whole lot of UV containing light exposure in common stress tests. And here we're doing something maybe even 30 times more than what you might see in typical tests. So this is just an example from these stress tests showing that it might be interesting or important to look at tests that include something like UV containing light exposure or greater extent of that. And I think that's maybe in alignment with what other groups are finding too. So to conclude, these were the three different stress case studies that we went through today. So the first case was impact of processing defects, where much of the problems were associated with the packaging materials. So we saw a loss dominated by delamination and resistive changes when that delamination progressed. The second case study was when the cell itself is unstable, but maybe the lamination process is a little better. So here we saw rear side passivation loss dominated by surface recombination. And then the third case study was when nothing's actually wrong with the sample. So stable module materials do exist, and that's good news for us in the future. So with that, thanks for listening. You can send me an email here or find me at my desk. And these are all the people who contributed, which is a lot of people. Thanks.
All right, thank you very much, Dana. It's very comprehensive, covered a lot of ground there. So I'm seeing a few questions in the Q&A tab, but I welcome the audience to please go ahead and enter any other questions they have. You can also upvote questions to have certain questions get closer to the top. If you're interested in those, I'll also welcome our 2 in-person attendees to raise their hands if they have any questions, and I'll let you guys ask those questions yourselves. Okay, so let's get started on some of these. So the first one I'm seeing here at the top is from David Miller. In the first study, which interface is delaminating? Do we think it's glass encapsulant or encapsulant cell?
Yeah, here, let's go back to those. So yeah, so for example, well, maybe let's find the overarching pictures. Yeah, for the glass ones, I think it's between the glass and the encapsulant here. You can kind of see that because my pointer's gone there, because you can see the actual surface texture of the glass. So that would be my vote there. For the transparent backsheet ones, maybe you can see here, there are 2 patterns of delamination when you illuminate from the rear side with the transparent backsheets. So it's hard to see, but like this one is more of like a circle, and then these ones kind of look like a dendritic growth. So I think these are 2 different surfaces of the delamination. I forget which is which, but one of them is between the encapsulant and the cell, and the other one is between the backsheet and the encapsulant. Yeah, hopefully that answers the question.
Yeah, I think it does, thanks. From Andrew Gabor, do you think the, sorry, questions are jumping around here.
Oh, sorry.
He's fine.
I'll mark them as answered. That's you.
Do you think the bus bar adjacent cracks would happen to the same degree for full-sized glass modules?
No, yeah, so if you're talking about the edge pinch problem, yeah, so here it's like we have a single cell and there's a lot of bowing. If you're just thinking about like the amount of surface area and how much area you're bowing to get to the corners of these mini modules, because they're like, I don't know, yeah, just 8 inches across. So they're not very big mini modules. For glass full modules, I think for a large part the industry has fixed this by using the double heat press plate laminators. And they don't use the bladder laminators that would pull down on the edges as much. Yeah, so that hopefully is fixed just with the instrumentation. And then also just the extent of how big the modules are. It wouldn't be as big of a surface area effect, I guess.
Yeah. I love this question from Ellie Palmiati. How common is it to have backsheets laminated backwards in modules?
Ideally not in a production setting, right? Like this is, yeah, as mini modules, it's probably like, even if they're made in a facility that would be making full modules, they're probably just not keeping track as well. And you have smaller pieces that can get lost. I'd assume if you're in a production setting, you have an automated setup where that's not going to be an issue.
Okay. Alan Liu, great data on half versus full cell degradation. What's your theory for the difference in degradation behavior there? Would thermal cycling be more detrimental to full versus half cells, do you think?
Thermal cycling for full versus half cells? Let me see what data we might be talking about. Are we thinking about probably here? Yeah, so with this test, there's such a small difference in the extent of degradation between the full cells and the half cells. I don't know how much I can really say that they're different. We saw, if you're really picking apart these tiny numbers, like the PUE and EPE ones have more degradation for the half cells, and the EVA one has more degradation for the full cells. So I think we don't have a clear trend that's only associated with half and full cells, and so it's hard to say what the difference here would be. Yeah, I mean, looking at the imaging here, I put a little note here that I think it's maybe more realistic to have interconnected half cells than it is to have a single full cell for mini module constructions, because you do get maybe some feedback between the cells in a way where, like, if one bus bar is carrying more current on one of the half cells, that affects how your next half cell is going to carry its current. And that's maybe a more realistic condition if you're trying to extrapolate to module level. Whereas these, like with the full cells, the gradient is always kind of from left to right, just associated with the resistance of the sideways busing ribbon. So there's a little difference there if you're just thinking about, like, you know, mini modules and the implications of mini modules for stress testing. But yeah, I think from this data, we can't say a whole lot about the implications of full versus half cells, and if one's going to degrade more than the other. Like, it's just too small.
Okay. The rear yellowness observation, was that seen after a specific step?
So the cells start out looking yellow.
Yeah, okay.
Yeah, if that's the question, like
I think so,
so this, yeah, like the cells start out with the same color, and I think the color itself is just associated with the refractive index of the coating. Like that's going to be related to the thickness of the nitride or the aluminum oxide, as well as the hydrogen content can also tune the refractive index. So that's not really going to change.
Okay.
Yeah.
Question from Takeshi Taigaki here. Are all the images you showed, are they all taken from the front, and do you see any difference on the back?
So we take all the images shown here are all from the front. We take the images on the front and back every single time. So we have too much data sitting around that basically tells you it's not that useful. The rear side images look basically the same. The usefulness of taking the images from the back is to just see the metallization pattern and how the degradation is related to, you know, the different shapes of the metallization. But in terms of recombination, the recombination happens within the silicon, and because of the thickness of the silicon, you're not getting much difference in, like, the pattern of the luminescence depending on what side you measure from.
Okay. From Sang Han, thanks you for the presentation. And he's not sure if he missed this, so it's good to clarify. The yellow versus blue cells that we saw in those modules, does that come from the silicon nitride? Is it like a thickness thing, or what's causing that?
Yeah. Here are we? Oh, here. Yeah. So I mean, it's probably there's a lot going on.
Yeah.
These images. One big difference is that the aluminum oxide has a different thickness. Usually when you think of the color, you would think more about the nitride because that's the anti-reflection coating. You can see, like, this nitride is deposited in multiple layers. So, like, there's a lot going on there. And I think people might do that if you're actively trying to tune the refractive index, or having a different hydrogen content near the back of the cell or something like that. I don't know a whole lot about cell processing, but I think that this layered structure, along with the differences in thicknesses, is going to be related to the color.
Gotcha. Okay, let's see. So Colleen O'Brien is asking if a wet insulation test is conducted after the stress tests, and have there been any failures? We didn't do wet?
No, we didn't do that.
Okay, so no wet insulation tests. From an anonymous attendee, are any edge seals used, or edge tape or frames? I guess they're asking for the lamination conditions. Do you want to cover that?
Yeah, so for the ones that have all the edge bowing, I keep like slipping going between sides. So like the samples that have all this bowing, I think the thought is that they don't have any support during the lamination and there's no like tape around the perimeter. And the ones that more optimized, I wonder if I can just scroll here and click one. Oops. Oh yeah, I can. Oops. It just goes slow. I just wanted to go to that slide that shows the differences between the ones that were optimized. Yeah, so like these ones that were optimized and don't have this edge pinch problem, those did have tape around the perimeter and supports that were the same thickness as the mini modules during the lamination. So even though they use the bladder laminator, you're trying to get around those problems with extra methods.
And then PID was excluded from this study, but do you want to comment on that a little bit more?
What about PID? Like what about?
Well, so they're
like
they're asking if we did PID, any PID testing on these samples.
Not that's included here. We had some PID testing just to see if it was different for the different encapsulants versus ones that had an edge seal with no encapsulant, but that is not included in these studies.
All right, I think that's the end of the questions that I have here. Either of you have questions for the room?
Is edge pinching something that is seen in commercial modules?
Yeah. Well, yeah, so I think it's kind of like anecdotally people around NREL have mentioned seeing it, and we have some sitting in the lab with cracked glass. Yeah.
Actually, the tough break report is out and it has edge pinch in it.
Oh, nice.
I can put a link to that in the chat.
Yeah.
Great.
I see more questions.
Oh yes, okay. So a question from Bill Gambogi. Are these differences in durability between glass and glass backsheet consistent with field data from the literature?
Unclear. I don't really know.
Yeah. And then another question here. So thank you for the presentation. Do you think that these results could be predicted using modeling approaches?
Which results?
They just said these results, I guess. More broadly, what could be predicted through modeling here?
Yeah, I mean, so there's a lot going on. Like there's so many different degradation modes, and I feel like you could model several of them. So we had, for example, just this solder pad degradation pattern. If I go back to this slide. Yeah. So that, for example, we can model just like things with electrical contact differences, like the imaging is super useful to see where the contacts are failing. And so you can import that into, or maybe not import it, but reproduce it as a model pretty easily. What else? I think like people are really interested in this like whole hydrogen redistribution thing. There's a lot of modeling efforts around that. Clearly with the yellow rear cells, there's some maybe relation to hydrogen redistribution, or yeah, like it could be in that realm of degradation modes, but that's something that's just so hard to understand at this point. So yeah, what else? What other, I guess if we go to all of our degradation modes that we've observed, yeah, plenty of modeling for just like corrosion processes. Yeah, and I think what does people have like studies ongoing for cell cracking, just the extent that cell cracking might matter for the performance. But yeah, so I guess like without being more specific, I'm not sure exactly what I should say about modeling.
Well, I guess people are welcome to email you as well if they have some questions on that too. So yeah. We talked about the thickness of the passivation layers. Are there any other factors that matter regarding, the
rear surface passivation?
Yes, yeah.
Yeah, I mean, there's different degradation modes that you can think about. Like, I think I kind of wrote a little bit of that here. Like there's chemical passivation modes from the hydrogen, but there's also just like the field effect passivation, just thinking about like the fixed charge in the aluminum oxide. So like that's something this like how the fixed charge responds to PID is like a big question. I feel like the imaging kind of reflects what you might see in a PID type of degradation mode that's affecting that field effect passivation. So there's a lot to think about. I think another thing here that I didn't really include, but that's an early observation, is the continuity of these passivation layers. Like with the yellow rear cells, depending where you look, things might look a little different. So that might be another thing to think about if there's any discontinuities or thickness variations that could impact like the degradation process.
Yeah. Okay, and the last question I see here, this one is perhaps a little challenging and somewhat broad too, but we talked about making more stable samples. But do they have as high power at time zero? So is initial efficiency, does that come at, does durability come at the cost of, lower initial efficiency? Or how does higher efficiency cells affect durability?
I mean, I feel like that's a pretty overarching question right now with
it
people
is.
like going to N-type cells and like
Right.
silicon heterojunction chasing like these higher efficiencies. Like ideally, you'll just fix the durability problem somewhere along the way and you'll have both, right? Like that's the dream, right? So I don't think that you want to say that, oh, we'll just stick to lower efficiency PERC cells because they're gonna be rock solid. I think you still want to chase the higher efficiencies and just fix the durability problem as you understand the degradation mechanism.
Mm-hmm. I did see one more question pop in here. So the question is, have you UV irradiated from rear side of modules for rear yellow cells in your study? And I guess maybe the question is if we see a difference between the blue and the
yeah, so this is the interesting thing for those yellow rear cells. We illuminated them from the rear and they degraded less than illuminating them from the front. So this is a problem with these cells of just like having their internal carrier density. It's not necessarily related to the direct UV exposure touching the back surface of the cell. So I think that's really interesting. So the reason that they degraded less with the rear side exposure, I think, is because they have a lower internal carrier density from the lower absorption from the rear side, so that coating is awful. And so they're just absorbing less light. They generate like 7 amps from the rear side or 10 amps from the front side. So the rear coating is not great. They're not absorbing the light. And in this stress sequence, it specifies the rear exposure is 1,000 hours instead of 2,000 hours. So so we did the rear exposure test. They degraded less than the rear, than if they were illuminated from the front. There are a few reasons for that. Mostly, I think, internal carrier density. You just need the charge there. Yeah.
All right, that is all of the questions that I can see. I don't think there are any further questions in the room either. So I think with that, we can go ahead and close out this webinar. I want to thank Dana again for presenting, and for everybody here for attending and asking questions. And we'll see you at the next one in January.
Yeah, there's a link in the chat to register for that January webinar. Hope to see you there.
Perfect, thanks.